Hello everyone, welcome back to my YouTube channel. My name is Nathan Rodriguez-Lynn, and today we will be talking about transformers and large language models. So the two main sources that we're going to be using today are Transformers Explained, Simple Explanation of Transformers by Code Basics, and Transformers, How LLMs Work, Explained Visually, DL5 by 3 Blue, 1 Brown. Let's get into it. Generative pre-trained transformers is a kind of neural network called a transformer that is designed to generate new text. Generative refers to the ability of the model to generate text like a human from some given input, and therefore it can be used for tasks such as summarizing, translating, and content generation. Pre-trained is the fact that the model has already been trained heavily on enormous amounts of text data before it is fine-tuned for specific applications. In this training, GPT models can learn a robust sense of grammar, syntax, semantics, and even some stylistic flair. A transformer, introduced in 2017, is the root of modern-day AI language models and has revolutionized natural language processing, or NLP, since it enables fast training and greater context awareness over earlier designs such as recurrent neural networks, or RNNs, and long short-term memory networks, or LSTM. Transformers function by predicting the next word in a sequence based on images or sound surrounding it as context. When presented with an input, a transformer model breaks it into tokens and calculates probabilities for each possible next token and then selects the most probable one to generate coherent text. The procedure is iteratively repeated so that each new token maintains the logical order of the text. Transformers differ from typical NLP models in that they do not process words sequentially, but rather look at whole sequences in parallel using self-attention mechanisms. This parallelization speeds up computation and enables improved long-range dependencies in text so that the model can produce contextually rich and meaningful responses. The input sentence is initially separated into discrete units called tokens that could be words, subwords, or regular character patterns. Tokenization is the most significant pre-processing step within transformers that converts text into an input format that the model is mathematically comprehensible by. Each token is then translated to a specific vector representation, capturing its meaning in numeric form. This vector representation is in a high-dimensional space where semantically similar words are placed closer to each other, which captures semantic relationships. This makes GPT models able to cope with many linguistic phenomena, including synonyms, polysemy, and relations between words, making GPT models very effective when it comes to understanding and generating text within different domains and styles. An attention block is a very important building unit that enables vectors to talk with each other, exchange data, and alter values. Central to transformers is the self-attention mechanism, through which they have capability of selectively focusing on important words within a sequence without paying so much attention to not so important words. In contrast to traditional sequence models, which obtain context purely from words neighboring a certain location, transformers may employ different levels of attention upon words within a complete sentence or paragraph. This flexibility allows them to resolve ambiguity, identify dependencies, and produce readable and contextual appropriate text. For example, in the sentence, "She went to the bank to deposit money," the attention mechanism distinguishes bank as a bank of money, not as a riverbank, because it considers nearby words. Deep learning algorithms like GPT-3 rely on backpropagation as the training procedure, which is something that we've covered in previous videos. Now, backpropagation is required to make the performance of the model better by adjusting the internal parameters or weights in order to minimize errors. This procedure includes translating the input data into arrays of real numbers, or tensors, that pass through different layers of the network. Each layer computes mathematical functions such as matrix multiplications and nonlinear activation functions to detect useful features. The model then compares its output with the actual output and calculates an error value. The backpropagation algorithm sends this error back to the network, adjusting the weights step by step to improve accuracy over time. This allows deep learning models to learn complex language patterns and generate human-like texts. Word embeddings is the process of representing words as vectors within a high-dimensional space and space directions carrying semantic meaning. Word embeddings preserve subtle patterns among words and enable the model to understand abstract ideas like gender, tense, and analogies. For example, in a well-trained embedding space, the vector difference between queen and king is similar to the vector difference between woman and man. This capability allows transformers to grasp nuances of language, such as antonyms, synonyms, and generate text in accordance with human wisdom. Contextual embeddings further refine this representation by changing word meanings based on the words they appear with, addressing problems with earlier static embeddings like word2vc and glove, which have given static vector representations that did not depend on context. The embedding matrix is the model's starting weights, and its columns determine the vector transformation for each word. The GPT-3 embedding matrix contains over 50,000 tokens, all of which are being mapped to 12,288 dimensional vector, meaning there are over 617 million trainable parameters in this section alone. This matrix enables the model to transform raw input text into a format that can be processed by the neural network in an efficient manner. In addition to static embeddings, transformers also employ positional embeddings, which provide word order information. Since transformers do not process text sequentially in nature like RNNs, positional embeddings play a significant role in preserving word order and grammatical coherence. These embeddings are then trained and tuned to improve performance on specific NLP tasks. The context window of the network restricts the amount of text that the transformer can absorb when it is predicting the next word. GPT-3 has a context window of 2048 tokens, which means it can observe and generate text up to this level before it forgets earlier details. For most tasks, this is more than sufficient, but for longer texts, the model may forget earlier conversation elements and generate inconsistent results. Context window determines the ability of the model to maintain coherence in long text and dialogue. Future models, like GPT-4 and beyond, will probably increase this context size to allow for better information retention in longer passages and improved performance in tasks requiring continuous reasoning and narrative flow. The unembedding matrix projects the last vector in the scenario to a list of values over the vocabulary for each token. This matrix is essential for translating internal numerical representation of the model back into text that can be read by humans. Once an input sequence has been processed, the model produces a high-dimensional vector representing the most probable next token. The unembedding matrix projects this vector onto a probability distribution across the vocabulary, selecting the most probable token. This is computationally expensive, as it involves comparison to tens of thousands of possible tokens. However, the unembedding step enables GPT models to generate fluent, contextually appropriate, and stylistically apt text. Lastly, softmax is used to convert a sequence of numbers into a probability distribution where each value ranges between 0 and 1, and the sum of all values equals 1. Softmax is a critical component of language generation because it defines the likelihood of each possible next token. The model injects randomness into text generation through the variation of temperature parameter used in the softmax function. Lower temperature produces more deterministic and predictable text, while higher temperatures increase randomness to generate more creative but potentially less coherent output. The logics, or raw output, scores before applying softmax play a role in determining the final text generation process, allowing for fine-tuning of output style and variability based on user preference and task needs. And that is the end of my Transformers and Large Language Models video. Thank you so much for watching, and I will see you next week.